This next example, if you can get through this whole problem and really understand every step, and then can repeat it on your own and get it, you've got it. Because this is probably the most complicated problem you'll have in physics this year. And it is the inclined plane with acceleration and friction problem. Okay, so there's a lot going on in this problem. So let's take a look at the problem in the book here. And I'll reread it, but it says a 62 kilogram person on skis is going down a hill sloped at 37 degrees. The coefficient of kinetic friction between the skis and the snow is 0.15. How fast is the skier going 5 seconds after starting from rest? So we're going to break that static friction and just assume that we're starting at v equals 0. And when you're 5 seconds into this, how fast are we going? Okay, so let's do this. Given. We've got a 37 degree slope. So here's the horizontal. Here's 37 degrees. I don't know how close that is. So here's the snow. And here's my skier. It's really easy to draw stick figures. You just go boom, boom, like this. Here's the body, the legs. And here's our skis. And we're always holding poles, right? So here's the little pole there. And we're going down the slope. And what do we know? Well, we're given the mass of the skier, 62 kilograms. We know that she's starting from rest. We also know the coefficient of friction, mu equals 0.15. And what are we trying to find? How fast is she going at t equals 5 seconds? Okay. Well, let's solve it. Well, I always like to try to start with what I'm trying to find. I'm trying to find the final velocity, and I'm given the time and the initial velocity. What has the final velocity, the time, and the initial velocity in it? The first kinematic equation does. So you have to use your kinematic equations that we talked about and look at it. Now, here's the deal. Here's a strategy. We're going to be able to figure out what the acceleration is. Okay? So, what is the initial velocity? 0. Do we know the time? Yes. 5 seconds. Do I know what the acceleration is? No. I don't know what the acceleration is. I'm going to need to find the acceleration in order to solve for the final velocity. Okay, you with me? So how do I find the acceleration? Well, I have to look at the forces acting on my skier and figure out the acceleration by using Newton's second law. So this means now I have to use the procedure. But now our procedure has been modified a little bit from last unit to include the fact that we're going to have to look for forces that are in the x and y direction and break them up into their components. And then use Newton's second law. So let's do that. Let's draw a free body diagram of the skier. I'll just redraw the skier like this. You can just draw the skier as a dot if you don't want to do all this drawing, but I always think it's kind of fun to draw my skiers. Okay, so here they are. And put a little scarf on them. So there you go. So what are the forces acting on our skier? Okay, I've got force of gravity, mg. Now, you've also got a normal force, but normal means perpendicular. That's why we call it the normal force. It's the force that exists between two surfaces that are pressed together. The skis and the snow are pressed together. The snow applies a force to the skis perpendicular to the incline, like this. So there's my normal force. Now there is friction in this problem. She's going down the slope, so the force of friction is going to be up the slope. So I didn't draw the slope steep enough. Let's make it a little steeper. And so there's my force of friction. So I got gravity, normal force, force of friction. Is there any applied forces here? No. That's it. But now look, here's a problem. Gravity and the normal force don't line up anymore. They're in different directions. Let me make this a little bit. So how are we going to deal with that? Well, what we need to do is this. This is step 2 of my procedure. Step 3. Yeah, I'm going to make the x direction go down the incline and the y direction be perpendicular to the incline. Now, why do I do this? To make the problem easier to solve. All right, so now I'm going to take this force now, and I have to break up the weight into its x and y components. Here's the x component, the y component. It's going to be perpendicular to the incline. And here's the component that is parallel to the incline. Now here's the number one mistake students make. I don't even want you to write this down. You can watch so you know what not to do, but I don't want you to write it down in your notes and then come back to it and think, oh, this is how you're supposed to do it. No. Here's what students often do. Here's your skier. I'll just draw the skier as a dot. And they draw the force of gravity like this, and then people tend to do this. They'll say, okay, here's the perpendicular component, and here's the x component. So here's the y component, and here's the x component. Tell me what the difference is between this triangle and this triangle. Yeah. Well, it's not that it's curved, it's sloped. Yes. This is now the x component of the weight. And it needs to be parallel to the incline. This is the part of gravity that's pulling you down the hill. If you draw it like this, now you're saying, no, the gravity's pulling you horizontally. Gravity doesn't pull horizontally, folks. It can pull you down a hill, or a component of it can pull you down a hill, but it doesn't do this. So don't do that. And also, look, mg, your weight here, this is always the hypotenuse. It's the hypotenuse. So these have to be the legs of that right triangle. This, you just made the y component here the hypotenuse. So don't do this ever. This is bad. Okay? Do that. Okay, now we're ready for step 4. Let's sum the forces in the x direction equals ma in the x direction. And then we'll sum the forces in the y direction equals ma in the y direction. So I'm just going to look in the x and y direction based on my free body diagram. If I look in the x direction, I'll say, okay, look, I've got two forces in the x direction. I've got the force of friction, and I've got this component of the weight. Now, what is this component of the weight? It's the weight times the sine of the angle of incline. So here's the angle of incline up there. Does that make sense? It's the opposite leg of this right triangle here. minus the force of friction. Because force of friction is in the negative x direction. If you're sliding down the hill, then the kinetic friction will oppose that motion. Equals ma. Is there acceleration? Yes, that's what we're trying to find, is the acceleration. So I can plug it in here. So now I can solve for A, step 5. A equals mg sine theta minus the force of friction divided by the mass. Now, do I know everything? Yeah, I know the mass, that's given. I know g. I know theta. Oh, but I don't know what the force of friction is. So let's figure it out. What's the force of friction equal to? What's our basic equation for the force of friction? It equals mu, our coefficient of friction, times the what? Times the normal force. Don't call it the weight. It's not even going to be equal to the weight anymore. Not in this problem. So do I know mu? Yes. Do I know the normal force? Not yet. What do I have to do in order to solve for the normal force? I got to look in the y direction. So let's do that. I look in the y direction. In the positive y direction, I've got the normal force. In the negative y direction, I've got this component of the weight, which is mg cosine theta. This is the adjacent leg. It's adjacent to this angle right here. And mg, the weight, is the hypotenuse. Equals, well, ma. Is there any acceleration in the y direction? No. I mean, is she flying into the air? Is she sinking into the snow? No. She's just cruising down the slope. So all of her acceleration is going to be in the x direction, none of it in the y direction. So this will be equal to 0. Now the nice thing is this tells me that the normal force will be equal to the weight times the cosine of the angle of incline. That's cool. Now that lets me substitute this into here. But what I'm gonna do a trick, and you don't have to do it this way. It's the way I'm going to do it because I hate adding. I hate using my calculator. So I'm going to say A is equal to mg sine theta minus the force of friction, which is mu times the normal force, but the normal force is mg cosine theta. And I think that somebody asked me about this part of the problem. So now I'm going to divide this by mass. Yes, question? Okay. Now let me take a look at this. Is there a factor in here that's in every term that will cancel out? Mass. Hey, they gave you the mass of the skier, but in this problem you don't need it. This is why if you're skiing with you and a little kid, you and the little kid are going to accelerate pretty much equally down the slope. There might be air resistance, and but we're not going to worry about that. And look, I've got a common factor here, so I'm going to do this one more time. I'm going to say, so the acceleration is equal to g sine theta minus mu g cosine theta. I'm going to factor out the g. And I get this little expression. Now I'm going to plug in numbers. I always plug in numbers at the last possible moment. Not always. Sometimes it's better to plug in numbers earlier, but 37, not 30. Minus mu times the cosine of 37 degrees. And when you do this, and multiply by 9.8, you get an acceleration of 4.7 meters per second squared down the incline. This is good. Now I can plug this into here. And I'll fit it down here. Zoom back out. So V equals A times T, but A is now 4.7 meters per second squared times 5 seconds. Seconds cancels the second squared. And I get my answer, which is, I'm cheating a little bit, I don't have my calculator, 24, if you round it off, 24 meters per second. That's fast. 24 meters per second. It's like 50, 60 miles an hour. And, you know, skiers do that. You know, have you ever watched the Olympics, which are coming up here? You go down a slope. It doesn't take long before you're going freeway speeds. Those people are nuts. But in any case, let's just review the whole thing here. And the problem-solving process. You know, first use give and find and solve. You know, and take your time with it. And say, okay, what am I trying to find? The velocity at t. So start with something that has what I need in it, and it kind of tells me what to do. Like, I want the final velocity, so I need a kinematic equation. Oh, I need to find the acceleration. That means I need to use Newton's second law, so I need to use that procedure of drawing a free body diagram, looking in the x and y direction, and then just solving for the unknown, and then getting my final answer. They're long problems. These are the longest problems of the year. You have to do the most. Any questions on this before I quit?